Okay, good morning, everyone. Thank you for being here. We are 3D-WE, and today we'll be presenting our research on 3D printing for wind energy. My name is Mona, and today I'll be joined by my group members, Jacob, Patrick, as well as Obadiah.
So additive manufacturing has recently been introduced to the wind energy field, but because it is so recent, there's not any research on how. So for our study, we'll do an analysis of quality and reliability on the 3D printed wind turbine blades and try to optimize their performance. And with the research that we provide, we'll be able to provide the optimal additive manufacturing parameters for wind turbine blades. So firstly, is this a problem? Yes. Energy from fossil fuels is a cause for 73% of human-caused greenhouse gases. And although wind turbine blades are clean energy, they are expensive and non-recyclable. So this supports that additive manufacturing still doesn't really have enough research to be implemented, making it a problem. And other people have realized this too, such as GE and UMaine. They've done low-cost thermoplastic wind turbine blade tips. For molds of wind turbine blades, smaller models have been developed and done wind tunnel testing, and also the failure modes of wind turbine blades have been researched, and fractal, thermal, and fatigue are the top three. So why do we want to do this? We know there's a problem. Other people realize that we researched this. So we want to be useful to help the aid or advancement of additive manufacturing and alternative energy fields. And by doing that, we reduce the percentage of human-caused greenhouse gases, and as well as using decreasing the amount of waste in landfill by creating recyclable wind turbine blades. So right here, we have the flow and elements of our design. So for the development, we learned about additive manufacturing, learned about wind energy, the do's and don'ts about it, and found out there are three key elements. So for integrity, we're learning at the structural capabilities of our 3D printed blade under different parameters. And then we're going to do our performance for reliability testing and try to figure out the life cycle of the blades that we printed. And then scalability, we'll do simulations to try to scale that up to a real size wind turbine blade. And then for our deliverables, we'll provide models and data for each one of these elements. And then our application will apply this to commercial use.
Okay, so now moving into our 3D printing experiment, we started by conducting research on the most important factors to model our wind turbines and identified the test that would allow us to accurately assess our prints. Our main scientific contribution for this phase was our application of a mixed level fractional factorial design, which provided us with our total number of prints, as well as our parameters, which were filament material, infill percentage, infill pattern, and layer height. Our main technological component in this phase was the application of both SolidWorks to model our prints and the Lulzbot Mini 2 3D printer to actually print them. Our 3D printer, along with our factors at each of the different levels, can be observed on the right-hand side. Next. So now moving into the testing and validation phase, we focused on dimensional accuracy testing, where we used a digital caliper to compare the measurements of the printed parts to those of the 3D model that we created in SolidWorks. We inputted and analyzed this data using our technology component JMP, which is a statistical analysis software, to observe the model fit and identify our statistically significant factors, which were filament and layer height. We also conducted surface roughness testing using the Keyence VR surface roughness machine, which generated thermal images and graphs of the average surface roughness across a part. Likewise, we statistically analyzed our data to identify our most significant effects, which were filament and infill percentage in this case. Now, moving into our mathematical equations, which we created, we utilized the factors which yielded the greatest statistical significance and generated 4 different expressions that will predict both the dimensional accuracy as well as the overall surface roughness of our different parts, whether they're printed using our PLA filament or our PETG filaments, which can all be seen below.
All right, so after we performed quality testing, we wanted to do reliability testing because we wanted to figure out how long our models will last. So what we did was we performed rotational fatigue testing using a lathe. Because we didn't have any state-of-the-art fatigue testing machines, we had to get creative and create our own reliability tests. So what we did was we designed new cylinder models with an equivalent mode of inertia as the original model using SolidWorks. Then we placed these cylinders on a lathe rotating at 300 RPM with an applied load of 16.5 pounds. And with that data, we were able to calculate how many cycles that it would last. And then doing some analysis, we figured out that infill percentage was really the only variable that had any impact on the model. So then we took our most reliable model, with the most reliable parameters. Then we fitted that with an exponential regression so we can calculate and predict the number of cycles at a particular stress. In this case, we did 15.5 megapascals, and we figured out that it would last about 47.1 hours. And then we also created a classification model, which was used to predict the model success rate within 150,000 cycles, and our model was about 100% accurate.
So now that we have our quality models done and we have an expected lifetime, our next step is using simulations to scale it up. The way we went about this was using non-dimensionalization, which uses Buckingham Pi theorem to remove units from variables to make them dimensionless, which allows us to scale it up. So to get the coefficients of lift and drag, we used ANSYS to simulate. If you look in the bottom right corner of that picture, the blue is the inlet, which allows us to shoot wind at various angles of attack on our blade, which is inside the symmetry, which has our material properties cut out as well as the geometry of it. So we ran a laminar flow, which is wind at an even pace and distribution at 500 iterations for each angle of attack. With this, we were able to get our KPIs, and as you can see to the graphs to the right, our best angle of attack to give us the most lift with less drag is an angle of 20 degrees. So our next step is to use the Reynolds number, which allows us to predict flow in various situations to scale it up. So Reynolds number, a key characteristic is the chord length, which is from the tip of the blade to the tail. And keeping it consistent, we found that the lift generated for our 6.2-inch blade was about half a Newton to a Newton of force. Taking into account that a vertical axis turbine has 3 or 4, you could expect it to have about 3 Newtons of generated force. Scaling it up, keeping it the chord length the same and scaling the speed down, it experiences about 1 mile per hour of wind, and it exhibits about 0.5 Newtons, but in reality, it would be producing about 15 Newtons of force in total. So here's a picture of the simulation being run at 20 degrees, which is our best angle. As you can see, the arrow shows how the wind is getting shot in. A and B, so A is a low velocity pressure, and B is a high velocity pressure, which is just showing how the wind is getting hit and affecting the blade and allowing it to generate lift. So some of our issues and limitations with this was we used a laminar flow, which is giving us strong rudimentary data, but to better simulate it, we would have used turbulent and shot wind at 360 degrees in both the X and Y, since vertical axis turbines can catch wind at any angle. So here's some of our project management. We all bounced around and pulled our weight as much as we could in every section. And some of the lessons we gathered from this was there's a lot of hiccups naturally in the lab with filament and printing, and we had to get creative and work around them and not give up. But we also got some insight into the complexities of additive manufacturing and wind energy. So for our future steps, or if another group takes it, we would suggest using the Creality mill to print larger turbine blades and then perform tests to see how much power it could generate, and then determine an optimal blade design or a system that can catch the wind better. So in conclusion, additive manufacturing is constantly growing, as well as renewable energy. We hope that our research that we've completed is useful and allows people to consider a new perspective, and anyone who uses our design to accurately get numbers similar to what we got. And we hope it excites you that in the future we can manufacture our own system to capture energy. So we just wanted to give a special thanks to Dr. Jafari, Dr. Blow, Dr. El Said, and Max. Any questions?